Yeah, thanks, Gregor. Hi, glad to be here. As Gregor said, I'm going to tell you today a little bit about my research on probabilistic neural fields. So first of all, let's state clearly that this is research in progress, so maybe I do not have rock-hard proofs for everything I'm going to tell you. It's more like presenting the basics, what I'm thinking, where this could go, so you can develop an open mind about different directions you can take with neural fields. So why does this subject interest me? So my research is quite diverse. At ENSTA I'm doing several things. So first of all, I'm still interested in vision, so in recognition of objects by vision, and especially in challenging scenarios. So like from a moving car, for example, where you have to detect by vision several interesting things like moving pedestrians or cars or traffic signs. And you may know this is not easy. I mean, there's in the real world where we are outside the lab, there's a lot of uncontrollability, there's a lot of noise. You can also see here already there is the noise of low resolution, which is always a problem, which makes object recognition difficult. So there is occlusion, there is rain, whatever. So it's basically very difficult with standard computer vision methods and machine learning methods to do a really, really good job on object recognition and detection. And that's why I'm interested also in basic neural learning techniques, trying to learn from how we perform, because we perform actually incredibly well. I mean, when you think what you're doing when you're driving, most of the time you don't notice, but you're doing a splendid job of detecting all those pedestrians that look like poles, or all those cars that look like boxes really because they're just a few pixels wide. And also you don't even know how low the resolution of your cameras here is. It's very low. So actually you're doing a good job when you drive. So I'm interested in knowing how this comes about, because evidently since we can do it, it must be possible, but just how is the question. And also I've, since several years, I'm starting to get really interested in neural fields, because it's supposed to be a brain-inspired principle for really explaining how things could work in the brain. So that's what I'm trying to think about. And especially when you think about object recognition, there's a very popular belief at the moment. I mean, it may be just a research trend, but there's actually good evidence that at least some of this could be true. Perception is very much like inference, probabilistic inference. So I guess you know a little bit of probability theory. So when you do probabilistic inference, actually the basic credo, the basic principle of when you treat things probabilistically is you don't pass around values. You don't say the value of this measurement is 1. You say rather you have a distribution of measurements where the value 1 has a very high probability and the others don't. So that's what you do when you do probabilistic processing. And the idea is that you actually pass around distributions, process distributions, give back distributions, and only at the final decision-making stage you really select the most likely interpretation. In that way, you don't lose any information on the way to the top if you do hierarchical processing. So this is what probabilistic inference is all about, and basically the inference here is you try to get the argmax of the final distribution. So basically you try to infer the most probable interpretation of your sensory input, which can be pixels or features or whatever you measure from the environment, and given the input and giving also other things, maybe context, and I'm going to come back to that in a second. When you formulate this in mathematical terms, basically is you want to find a posterior distribution, the distributions over interpretations I, which are supposed to be countable, given the input. And basically this is a very simple formula, and this you do, mainly the main tool here is Bayes rule. So you can not only represent distributions, pass around distributions, but also manipulate them by using Bayes rules. So if you want to know the probability of sum of A given B, you can apply this formula, and it's guaranteed by the theory of probability that the outcome will again be a probability. And if you look at the formula closely, basically this amounts to multiplying distributions. So this is all very abstract, and actually you don't need to retain much of it, because I'm going to skip a slide which I shouldn't have skipped, sorry. I'm going to make it more clear by an example. So this is a classic example from computer vision literature. It's from Moshe Bar, 2006. Here you have two images. where you see two different scenes with the same blurred object in it. Now think about what this could represent. I mean, most of us would agree that on the left you see a hairdryer, and on the right, well, it could be one of many things, a drill probably, or a gun. Well, a gun is less likely on a work table, but that's the point. It's less likely. So the only thing you know for sure is this not very sharp pixel pattern. Can be anything. However, your brain automatically supplies from the context that on the left image must be a hairdryer, because you find hairdryers in a bath. And on the right image, you are not sure, because actually most probable interpretation for most of you would be drill, because on work tables you find drills. So your brain has automatically taken into account the context. So your brain has actually done a Bayesian, has applied Bayes rule. It has said, okay, the probability for this vague pixel pattern being a gun is the probability of having this pixel pattern if it were a gun, which is the same for all alternatives because it's always the same pixel pattern, multiplied by the a priori probability of finding a gun in a given context. And evidently you can see if the pixel pattern is indistinguishable, it's just this term. This will make sure that the right decision is selected. So that is to say, in the bathroom you say hairdryer, in the worktop scenario you would say probably drill or gun. So this is an example of what Bayes rule does. And actually when you do real world computer vision, this is what you apply all the time, because this ambiguity problem stays with you. For example, I'm trying often to detect cars in very complex cluttered sequences. Now when you look at inner city sequences, a car, this is basically a rectangle, a blurred rectangle, which can resemble very much a window. If you rip it out of context, a car is exactly the same pixel pattern as a window. So the only way to distinguish the same pixel pattern is to know, okay, where is this pixel pattern found on the road? Then I guess it's a car. If it's up on a building, it's probably not a car. And this, the same thing applies for pedestrians, for many other things in which you encounter in real world vision. So actually, these kind of Bayesian computations are everywhere. And without them, it is a firm belief of myself and many other researchers, you cannot really do good and performant computer vision as our brain does, because evidently we do it very well. So the question is, if we do this all the time, or apparently we do some approximation of it because our brain performs flawlessly in all these scenes, which our computer vision algorithms don't, the question is, how does the brain approximate this probabilistic computation? Because evidently it does something like that, otherwise it wouldn't be able to get all these results. And that's what made me think about how to replicate this behavior with neural fields. Because neural fields were in the beginning, in the 70s, when the model was proposed, was considered to be a generic model of the function of cortical layers. So if one of the function of cortical layers is to somehow in some way approximate the integration of probabilities, then neural fields should be in some way able to do this. And the question is this true? Is our model complete enough? Can neural fields represent actually probability in some way? And this is what I'm going to talk about. So, the first and basic issue is actually how to do inference. Is there an inference mechanism in neural fields? So given an input, is there a mechanism to try to deduce the most likely interpretation of that input? Does it exist in the dynamics? And I'm going to do all these things step by step. I'll just be giving you an overview here. Secondly, is there a way to represent probability? So if there is a way to infer the most likely interpretation of an input, can I represent a probability for this interpretation? Is it possible? And the third question, actually, that is the most basic question, given all these basic if all these basic mechanisms would exist, is there a way in which neural fields can represent really distributions over values? I mean, you know by now, I guess, what neural fields do. And that at least seems doubtful that they could represent directly a probability distribution, because you know that a neural field converges to an attractor state given an input, and that is rarely a distribution. That is a localized thing. So where's the distribution? It's not easy to imagine. So I'm going to try to elucidate some ways to get around this and still represent all these things with neural fields. Please interrupt me at any time. We have a lot of time, so I can explain on the fly if it's necessary. So first of all, is there an inference mechanism? And I'm going to say yes, but for this I'm going to take a small detour. Also I'm going to show some formulas which will be ugly, but don't worry, it's mainly for illustrating the mathematical rigorousness of what I'm going to tell you. So I'm going to first talk about Lyapunov functionals. A Lyapunov functional is a functional that can be defined for any kind of, for a dynamical system. And it maps basically the whole state of the system to a real number. In more physical terms, this is actually an energy functional. So if a Lyapunov functional exists, this is not guaranteed for any dynamical system, but if it exists, it is kind of an energy. And for those of you who know a bit of physics, energy is something that is minimized. Any physical system tries to minimize its own energy. So basically, what a Lyapunov functional does, if the system, the dynamical system, evolves according to its equation of evolution, for example, the equation of evolution for neural field, then the Lyapunov functional will always decrease until it reaches a stable state. And there are all kinds of mathematical guarantees. So a Lyapunov functional must be strictly decreasing. It can at most stay constant, but it can never increase on its own. And it must be bounded from below. So there are some kind of mathematical guarantees to tell you some stable state will at least be reached. This is what a Lyapunov functional gives us. And more importantly, if you can write down your Lyapunov functional, you can partly understand what the system does, which is not always very evident from the differential equation. So you're going to see this on the next slide. Not every dynamical system has a Lyapunov functional. In physics, evidently, every dynamical system has one, because energy is something you can almost always define in a meaningful sense. But if you write down an arbitrary differential equation, it's not clear that such a functional, that an energy functional exists. So this is unclear, but it has been shown that dynamic neural fields do have an energy functional. And it has the following very simple form. So first, on the top line, you see the basic differential equation of the dynamic neural field model, which I just put there to explain my notation. So you have the standard terms, the state z, the input I, and the lateral interaction term, which is the integral over the lateral connection weights w. So I guess you know that pretty well by now. Then the energy functional for the dynamic neural field model is given on the middle line, which looks very complex. And actually we can rewrite this a little bit, which is what you see in the last line. This is just using some shorthands and noting that any integral of two functions can always be considered a scalar product. So I reformulated this exactly in the same way as scalar products. So what you see the energy functional is composed of three terms. First of all, it is the similarity of state to input. Because a scalar product is always about similarity. If it's 0, perfect similarity. If it's -1 or if it's infinite, no similarity. So you have three scalar products. First of all is similarity of state to input. Second one, and this is the tricky term, is similarity of state to the lateral interaction generated by that state. So in other words, how is the current state compatible with lateral interaction? And third term is basically the scalar product of z and a monotonous non-decreasing function of z. So basically this is always a positive term, which will be high if activity z is high. And this energy is minimized during the normal course of dynamics. So now we can see a little bit better what a neural field, yeah?
So could you repeat the second term?
The second term. So I'm too small. This is just a shorthand for the convolution of the field state with the lateral interaction kernel. Yeah? So you try to find the similarity between the field state and the field state convolved by lateral interaction. So if the field state, for example, is perfectly aligned with lateral interaction, then this term will be high. Or let's say, if there's a lot of interaction in the field, if there are 3 bubbles that try to kill each other, then there will be a lot of interaction in the field. If, however, there's no interaction in the field, that means there's just one bubble which doesn't kill itself because it's in the excitatory regime. So this means basically how much are things in the field conflicting with one another. It's hard to explain in normal words, but that's what it does. How much, the measure of conflict. Yeah, and if you accept that, I hope, does that answer somehow your question? Okay. If you accept that, then it's very easy to see what a neural field actually does.
Yeah.
Yep.
In the antifunctional, is it really Z with a sign that enters there, or is it the sigmoid Z?
No, it's Z with a sign. So that is always positive because it's already passed through a sigmoid. So this is Z, this is the state after the sigmoid.
Ah.
Yeah. Oh yeah, that is wrong. Sorry, yeah. So yeah, there should be a sigmoid. So that is actually the state passed through the sigmoid. That's it. Sorry. Yeah, that's my fault. So what you see, but it doesn't invalidate anything I said. It's just a notational glitch. We try to minimize. First, we try to maximize similarity of state to input. We try to maximize similarity to self-interaction, and we try to minimize activity at the same time. That's what the neural field does. So it tries to find a solution which is maximally compatible with the input, which is maximally compatible with its own lateral interaction, and with this, which is as inactive as possible. So this is just to see that the activations do not grow forever. And now actually, this explains pretty much what this differential equation does, because at least for me, when I saw it first, it was not evident what this equation did. But if you have the Lyapunov functional, you can gain at least some understanding what happens. And you can also see that the two terms, first terms come with a minus sign, so they maximize. The others, the other comes with a plus sign, so it's minimized. So it's very coherent. So now we have seen in this equation the second term, the similarity to the self-interaction. This is actually the term that more or less drives what the field does, and it will evidently depend on the lateral connections. So usually when you do neural fields, you do this kind of lateral connections, which is the standard Mexican head profile with a global position. And when you think about it a bit outside the way it's normally done in the neural field domain, this is actually a data model, because it determines where the neural field converges to. So the lateral interaction tells you where the equilibrium state of the field will actually be. This is nothing new. This is clear. If you put a different kernel, a differently sized kernel, for example, there will be different solutions. But I think you can think about totally different kernels. It doesn't have to be a Mexican head profile. It's just when you think that a neural field converges to a state which is maximally compatible with input and lateral interactions, then you could think about, well, adapting your lateral interaction to the data you have. So the lateral interaction actually describes what kind of data you expect. And I will show you how this works in a video. Yeah. So if you take the standard Mexican head kernel and you give it an input that is a single Gaussian, then it's very clear to see that this input is maximally compatible with the data model, because actually a single Gaussian will not create any self-interaction. It will not create any suppression in the field. It will just reinforce itself. And that's what happens. So on the left you see the input, which is a single Gaussian. On the right you see the convergence of the field. I'm sorry, this is not as flashy as Gregor's tools. but I guess you see what's happening. So the field converges to a state of a single Gaussian at the place where the input is. So this is nothing new. You know this. However, what happens if we put in two Gaussians far away from each other, so there are no fusion effects? These two Gaussians will fight to the death because they are not compatible with the data model. Actually, this Mexican head data model tells us there should be one Gaussian of a certain size. And this is an assumption that is totally violated here. So the neural field will try to converge to a state where the assumption is no longer violated. And that's what you see, what happens. You see the right Gaussian, because he's a tiny, tiny bit smaller, will get, in time, suppressed by bilateral interaction. So here we have arrived at a state which is again compatible with the data model, and the neural field has found it. And actually it has chosen the left Gaussian. It could have also chosen the right one, but the right one was slightly smaller than the left one, so actually it was less probable, less compatible with the data model. So you choose always the Gaussian that is more compatible with the internal model. And that's what the neural fields in this example actually have done. So now I try to continue. So I've tried to motivate that there is, in some simple way, at least I have to admit it's very simple because I just showed for Gaussian inputs, and that's pretty much all you can do for now. But I guess Gaussian inputs are not very uncommon for neural fields, so maybe it's not so bad. So there is an inference mechanism that is possible, that is capable of recovering the solution that is most compatible with its internal data model and with the input. That's what you have seen. We have also seen, or I've tried to convince you, that it's actually the lateral connections that describe, that parameterize what kind of solutions we expect in the input and what kind of solutions we allow. If there are solutions that violate this model, there will be competition until such a point where the solution is again compatible. And since the neural field is something continuous, so the evolution is continuous, actually the compatibility, even if a Gaussian is suppressed, the compatibility will be as high as possible to the input. So it tries to maximize both similarity to data model and similarity to input. And here's the link to statistics. If you now say the data model that I have encoded in the lateral connections matches the statistics of the data, so if there are really only Gaussians of one peak in the inputs, then this is actually something that is linked to statistics. Then the neural field infers the most probable representation of the input. And that is a point here which should be maybe expanded a bit upon. Of course, this kernel is not learned, but if I want to make sure there's a coherence between where the field converges to and what kernel I have, then the kernel should be learned from data. And of course, this is not very hard to imagine that you could do this. I didn't. But if the kernel is learned from data, if the kernel represents the statistical properties of the data, so if I learn that there always should be really only one Gaussian, then I have a connection to probability. So in this sense, we can say a neural network with a dynamic neural field with a correctly parameterized kernel that fits the data infers the most probable interpretation of the inputs. Any questions so far?
I think confused about what is the distribution and what is the space that you estimate. So I thought that the distribution, so the analogy probabilistic is the distribution of activation. And then when you say it selects the maximum it's a whole distribution that resides. Just talk about where the peak location is.
I'm talking about two things here. So the input can be a distribution over possibilities. I have maybe two Gaussians with different peak strengths. That can be a distribution. The neural field selects the one solution from this distribution which is the most probable one. So what I get out of the field here is not a distribution. It is just one state. As this is what neural fields do. Yeah, the location of the peak is what I get out of that. I mean, there's more to it, but this is basically what I get out, yes. And how to get back the distribution will come in a second. But I just want to motivate, there is an inference mechanism that from any distribution that comes in the input, I can infer the most likely interpretation. Okay, this was not it. So the second problem is, now that I have inferred the most likely interpretation, what is actually its probability? Because as Gregor correctly said, I want to, in the end, I want to have distributions. So let's go back to the examples I showed you. When you look at this example, where I have just one single Gaussian peak, I would like to draw your attention to the iteration count here in the bottom. Let's see when the field converges. So when the peak on the left reaches a value of close to 1. Well, iteration 80 maybe. So this is one situation. The other situation is when I have two competing peaks. Let's see when convergence is reached here. Evidently, since the two peaks fight, this takes time. We all see that. So, iteration 135. So you see, whenever there's a violation of the data model in my input, actually the convergence to the stable state, which is the most likely state, takes longer. And this is actually a currency which I tend to use as much as possible in what follows. If I can get the slides to display. So my proposal is, or my idea is for representing probabilities with neural fields is that we should more exploit the dynamics. This is, after all, dynamic neural fields. So the dynamics of convergence tell us, apparently, if there's a lot of conflict in the field, then the convergence will take much longer than if there were no conflict. So I can not only infer the most likely interpretation, but by looking at the latency of this attractor state, I can also tell something about how compatible was this input actually with my data model. So this is nothing else but probability. I tell here, by the latency, the neural field tells me how likely does it consider the current input. And also from Lyapunov analysis, you can well, this is just an analogy, but if you think that the field has to traverse a much longer path until convergence, basically you can also guess that it must take longer. This is not a rigorous proof because things can also be very conflicted, but they have a very fast convergence. But in general, what we see is when there's a lot of competition, when a data model is violated, when an input is less likely, then we have a lot of latency. So that was the second point. And I want to illustrate this with some simulation results. Do not look too closely at the axis here. What is important, this was a neural field to which I submitted several. Yeah, sorry? Oh, yeah, that could be nice. Thanks. Oh, yeah, thanks. Yeah, cool. So what we see here is a neural field, first of all, to which I put two Gaussian inputs with a peak difference of delta A, so just what you saw in the videos. And that corresponds evidently to different to situations of different conflicts. So if delta A is 1, that means one Gaussian is full strength and the other is absent. If delta A is 0, there's two Gaussians of equal strength. And you can see when you look at the latency in simulation ticks for very low for very low differences between Gaussians, you get a very high latency. If the difference gets large, the latency decreases. So there's a clear monotonous relationship between latency and, let's say, conflict or probability of the input. And this doesn't hold only for this kind of conflict, but also if you have just one Gaussian in the input, but whose amplitude is non-maximal. This also violates the data model. The data model supposedly have one Gaussian with maximum peak. So you see when you reduce the peak strength of the single Gaussian at the input, latency goes up very strongly. So these are two possible kinds of violating the data model, and all the time the most likely interpretation is found at the correct place, so the model converges to the place of the stronger Gaussian. but it will take different times. And this is my measure, my proposal, that we could interpret this time to convergence as some measure of the probability of the state that the field converges to. Yep.
Delta A.
Yep.
Is the separation of the amplitude between.
No, this is the peak, the difference between the height of the amplitude. So how strong are the Gaussians? The spatial separation is always the same. They have just different strength, like in the video you saw. So if they have the same strength, they will fight for a very long time until noise gives advantage to one or the other. If they have totally different strength, well, then the stronger will very quickly win the competition. So to summarize, well, I basically summarized it already. The only thing I want to really point out is when you interpret latency as some kind of associated probability, then you should be aware that this is basically something you get for free. The latency is inherent in the dynamics. I changed nothing in the model. This was there. The question is just how to parameterize the model that the latency you can always observe is in a range where you can observe it. So if you don't parameterize correctly, if you set your H a little bit too high, or your lateral interaction strength not correctly, then the latency will be there, but will be very, very, very tiny. So this is actually the only challenge, to find parameters for which the latency becomes apparent. But it's always there. So my idea is, if it's always there, why not make use of it? And now, to the last problem, and I think this is the most difficult one. Given that we can, for any input, represent the most likely interpretation, or find the most likely interpretation with a neural field, and the associated probability of that interpretation, well, that is one point in the distribution. So, but what I would like to have the probability of all possible interpretations of an input. This is what Bayesian, what probabilistic inference is all about. And it seems that this is not possible in a straightforward way, because the field converges to its localized attractor state, and any information that might have been in the input is eventually suppressed. It's no longer present in the field states, as you saw in the videos. The second peak gets killed, it's no longer there. So what can we do? Actually, what we do here is from an application point of view, this is not so bad what we are doing. I mean, because I can infer the most likely state given the input, but I can say if this state which I infer is the most likely, but if its probability is very low, I can still exclude it. So when I have two Gaussians, then it might not be two Gaussians of equal strength, then it might not be very useful in practice to select one if they have almost equal strength. Because then it's a bit arbitrary, it might depend on noise. And then this is a result I shouldn't use, and I can do because the latency of the associated solution will be very high. So this is actually something that tells me this is a result you cannot trust. So be careful. So even if I cannot represent the whole distribution, I can represent, let's say, the first mood, the most important mood, and its associated probability, which I can use to discard a solution if it's too low probability. So from a practitioner's point of view, this would in many cases be already enough. But this is not the end. What we would actually like to do is not recover only the most probable interpretation, but maybe the two most probable interpretations if it were possible, or the n most probable interpretations. I mean, I don't need all of them. In practice, when you do object recognition, you have like 2 or 3 or 5 candidates which have a significant probability, and the rest you can forget. So if you again can get the 3-4 most likely interpretations, we'll be fine. And actually now I will tell you how we could do this. Maybe some of you know a bit of cognitive vision science. There is an effect which is everywhere in the human brain. There's an effect called inhibition of return. So this means when you have visually attended a certain location, it gets subsequently suppressed. You can really show that there is suppression going to that point, which prevents us from focalizing this point again in the near future. And that leaves us open to focalize, to put our focus on other points. So this is a Klein 2002 paper. I don't know when it was, but this is a classic paper in vision science. This is very well established. So my idea is, why not do a similar thing with neural fields? If I, just a simple example, if I had an input, which is a distribution, which tells me, okay, the input can be either a Gaussian on the left, or with less probability a Gaussian on the right, well, what the field will do initially, it will converge to this state, because the left Gaussian is stronger. And it will depend on the difference between the strengths of these two Gaussians, how long that takes, this convergence. Then I introduce an inhibitory layer. Gregor does that very often in his work, which has a bit of a longer time constant, so it acts as a kind of memory. So the inhibitory layer is excited by the solution that comes up, and then sends feedback and kills a part of the input that was responsible for the current solution. And I guess you see how this is going. If the input that is responsible for the current solution is killed, well, the other solution has a chance to come up, which is what happens. So I have another solution coming up, which corresponds to the second Gaussian, which can then, in turn, goes to the memory field, in turn gets inhibited, and if there were any other components in the input, they could have a go. So in this sense, I cannot represent a distribution over values as it is present in the input in the same field at the same instant. But I can again use the dynamics. I can say, okay, I can represent them at different instants. I can say, first of all, the most likely one, and do a processing upon that. Then, the next most likely one, and do processing on that. And so on and so on. So basically what I get is a temporal sequence, temporal sequence of slides, temporal sequence of attractor solutions, which will represent, and this is the important point, in descending order, the interpretations of the input. In descending order of probability, I should have said. So basically, again, I have no way to represent any spatially extended distribution in a neural field. This is just not possible, I think. But again, I can use the dynamics. I can extend what I cannot do in space into time. As I did with latency. Latency is a temporal effect which can be used to express probability. And again, the sequence of attractor solutions in time can tell me something about the distribution properties of the input. And the fact that this is sorted by probability is, from a practitioner's point of view, invaluable. If you want to do object recognition, you take the first three most likely inputs, and the rest you switch because you don't have time for much more anyway. So this is perfect. So in this sense, if we go beyond a single neural field, but if we build circuits, and they are simple circuits, those circuits are well published, they exist, they work, then we can actually represent real distribution in neural fields. And so basically, I've already clicked again too much. So basically, this is my proposal for how to make neural fields probabilistic, or basically, I do not do anything to them. I just interpret what they do in a different way. The lateral connections represent a model of the data I'm expecting. And of course, it's up to me to choose a lateral connection model which will be convergent, which is something that has to be ensured, and which will accurately model the kind of data I'm going to have. This is something that should be typically done by learning. Then, if I have that, the attractor solution will both represent the most likely interpretation of the input, so it will do inference, and by its latency, it will also tell me how probable it thinks this most probable solution is. And then, simple circuit building can give me the sequence of descending probabilities over time. This is what I would do for implementing probabilities in neural fields. And evidently, well, I have done already part of it, so there's a few papers I have published on that. Evidently, this is just the beginning. So I've shown all this for very, very simple inputs. How does it work for more complex inputs? If there are more Gaussians, if their inputs are not Gaussians, for example, what do we do there? I don't know. We have to see. The point is, to my feeling, when we do dynamic neural fields, we made too much use of the fact that they are dynamic. So the dynamics should work for us rather than make it a bit more complex for us. So this is what I'm trying to do. Also, basic fact, to the dynamics as they were proposed initially, I have not changed anything. I've just found a parameterization where I can see the latency effect in a way that can be measured. So it's still the same model. It has to be just set to a working point where the effects that I'm describing occur. And when you go a step back and look a bit at the broader perspective, you can say, initially in neural fields, we have space coding. So the place of an attractor solution encodes meaning. So it says dog or cat or move your arm to the left, move it to the right. Has a metric dimension is, say, value is 0.5, value is 0.6. So the place of the attractor plays a role. And here we change a bit to having a spatiotemporal code. So not only the place plays a role, but also the time until the attractor comes up plays a role. And this is also not uncommon in biological works to have these effects, at least on very low-level vision phenomena. This is very, very well known. Although there's always discussion how far this can go. So temporal coding, this is a very, very wide issue in neuroscience. Many people think are very radical in this aspect. I would not propose anything radical. I would just say if a neuron is unsure, if a neural field is unsure about what it gets as input, it takes longer. This is the basic credo which I'm trying to propose. And that means that the most confident signals come first. And this is for a behaving system is of course crucial. If you want to act, you have to act rapidly. You cannot say, okay, let's wait until all the alternatives are in. Sometimes you have to act now. You have to decide whether you should run away or whether you should brake, for example, in a car, or whether you should not brake. So sometimes you have to act onto the first result you get. Cannot wait for others. And then if you have to do that, it's best if the first signal is actually the most confident one. That helps you in your behavior. Yeah, this is some of the things I think about these issues. Yes?
Ask for the representation of probability to be useful as a representation, do you think that it needs to be usable for some other calculation? For instance, if somewhere downstream you want to use a base formula again.
Yep.
How can you use the latency that way?
Good question. Thank you for asking it now because this is something that I want to present in an outlook. I tried to keep it it was not simple, I guess, but I tried to keep it at a manageable complexity level. But there's actually a way to do exactly that. Imagine, well, let me maybe use the blackboard. If you had a neural field here that would take its input from two downstream neural fields. So let's suppose here's a Gaussian solution, attractor solution, and here's another. But suppose these two have different latency. So suppose this was generated from such an input, and this was generated from such an input. So here with strong Gaussian, very weak Gaussian, strong Gaussian, almost as strong Gaussian. So this will have a positive latency with respect to that one. This one comes later. Then if you put that into a downstream neural field, intuitively you can imagine what happens. The first peak gets selected. So this is also a very biological principle. Whichever input comes first to a layer gets a competitive advantage because it has already time to spread its activation while the other input is not yet here. So, and that translate into a higher pre-activation. So when this one arrives finally, there is already a comfortable activity here which allows to suppress the other. And this is actually what I experimentally verified for a two-layer neural fields model exactly like this one. So you can say, well, how do I explain this? First, I should let you see the axis. So if you have here, I have plotted the delta t between the two inputs that come to this field. So suppose there are two Gaussians with a delta t between them. If the delta t is 0, if they come at the same time, then the latency of the attractor solution will be infinite. because it will take forever until the field converges, or at least it will take a very long time until numerical imprecisions or noise will give preference to one peak or the other. So at two equal Gaussians at the same time, no decision, which makes sense because you can take no decision. Both are equally probable. And if, however, the latency is the time difference is negative, so the green one comes first, then it's the green one that gets selected. And the more first it comes, the earlier it comes, the smaller is its latency. Oh, did I explain that correctly? So if the first peak comes much earlier than the other, than the second, not only will it be selected, but it will be selected faster. This is the point. So if it comes almost at the same time as the second peak, it will still be selected, but it will take longer because there will be less buildup of pre-shape and there will be more competition with the other until the other is killed. And this is totally symmetric. So if you take the other peak, if the other peak comes first, then it will be selected first. So, yeah?
Sorry, continue what you were just going to say, and then I'll ask Kevin.
Go ahead, I was finished.
It seems like there's a compatibility between this and the Probabilistic model, like the 2009 object recognition one.
Exactly.
It's using the speed of the recognition of like particular dimensions to like sort of help the other dimensions that are struggling. So if you've got like an instance of a particular object that is sort of like not quite the same as one you've been like previously trained on, then like the dimensions that are sort of like easier, like say color, let's say that's recognized faster than like ratio or something like that. And so it sort of like pulls aspect ratio like over with it. Okay, and so it seems like you compare the way the perspective that you're taking here with that particular model, then there should be like a congruency. I don't know if that's
No, actually this is modeled after that model. So in the papers I published this year, I've used a very similar kind of paradigm. And actually I did not invent this mechanism, this was there. They mention it in this paper. It's just I propose a concrete probabilistic interpretation for it. So yeah, it's totally compatible. The only thing I do differently from the Faubel-Schöner paper is that I use connection weights between the layers for doing object recognition, for integrating different field inputs. But the other, they use some kind of two-dimensional fields where which are basically a weight matrix if you want. So yeah, it's compatible. And now, so basically to summarize this, not only can we represent probability, encode probability, and represent distributions, but also downstream fields can integrate inputs coming from different upstream fields and decode the latency in exactly the right way. So again, for this mechanism here to work, I do not have to change anything to the model. I take the same model. It's just I take a parameterization where the field is sensible to these small time differences, because for wrong parameterization, even a large delta t will give just the same result. Has to be right. And that is, of course, a big issue because parameterizing neural fields is tricky. So here there's work to be done. How do I automatically find parameter values that would allow the latency effects to show up? Because that would depend on the data. And this is something where I believe that homeostatic methods of adapting the field variables to the statistics of the input automatically could help. And well, I have done some tests and it seems to somehow work, but it's not easy because of the nonlinear nature of the model. You change one parameter a little bit and it goes ping in totally another direction. So care is needed. But as I said, this is research in progress, so I'm on it. And the last thing I want to mention is I have now talked about the basics, so how to represent distributions. I did not talk at all about how to manipulate them. Yeah. So how to combine two distributions, for example. And here, actually, I think the idea of pre-shape is a crucial one. So if I have two peaks in this scenario that come at different latencies, if there's no pre-shape, they will fight it out fair and square. But if there's already pre-shape from somewhere else, of course, this one, if there's pre-shape already here, this one will already have a competitive advantage. So this will translate into a higher a priori probability to get selected. So even if it comes a bit later, it might be selected if there's sufficient pre-shape. So this is for me also a link to how something resembling Bayes' rule could be implemented. I mean, I'm not a purist. I do not aim to implement these things exactly, because I'm very sure that this will not be possible exactly. But we don't care about exactness. We just want something that is good enough in practice. I don't think our brain cares about exactness. It just wants to behave without being eaten or dying. And that's the point. So I think with this we can approximate well enough. And actually that was the last point I wanted to make. Yeah, as I said, I'm still on it. And that was all I wanted to tell you. I'm open for your questions. And thank you for your attention.